Start recording. Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on Twitch. No engines, no libraries, it's just us and our little typing fingers typing away. And right now we are typing on sound mixing. I guess to be a little more specific, we pretty much did all of the sound mixing stuff we wanted to do preliminarily. And we've got sounds playing, we've got sound streaming, we got pitch changes, we got volume ramping and panning, stuff like that. But one of the things that I kind of wanted to do with it is just drop it down to be wide vector. So it's, I wanted to basically have it in SIMD like our renderer is, just so we could see how that affects the architecture at all, just to make sure that there's no sort of snafus in there. Because it's pretty simple to do, it's not a huge onerous undertaking. So I wanted to kind of do that maybe today, and we don't have to go overboard with it. I'm not really even thinking about it as us optimizing the sound mixer or anything like that. I'm just strictly want to make sure that, if we decide to do 4 sample at a time wide version, that it's all, kosher. So I'm going to go ahead and do that, I think, today, just so we can get a feel for it. But before I do that, let me just mention that if you have pre-ordered the game on handmadehero.org, you can download the source zip. And today's day 144, so what you want to do is take day 143 source code and unzip that into a directory, because if you do that, then you will be exactly where I am right now, and you can follow along with me. So, maybe that's something that you like to do, and if it is, that's what we're doing. So day 143's source code is what you want to look at there. In fact, let me just make sure that I'm right about that. The machine kind of logged itself out the other day, so I had to start it up. Yeah, so 143 was the latest source zip, so there you go. All right. So let's go over here to the sound code. We've got it kind of isolated in its own file. And this is the entirety, really, of that sound code, right, that we're looking at here. It's this output playing sounds function. And it really does pretty much all the stuff that we wanted it to do. It's basically got everything in there for now. And so what I'd like to do here is I'd like to just take a look at making this into SIMD. Now, if you don't know what SIMD is, or what SSE is, I apologize. I'm not going to explain it again because I already explained it in detail before when we did the render. So if you didn't see that, go back and watch that in the video archive, the SIMD introduction. If you're lost with what we're doing here, go back and watch that, and I explain it in quite a bit of detail. So I'm not really going to mention anything other than brief, refreshing stuff as we go through it. I'm just going to assume everyone's seen that, or will go and see that if they want to know. So if we come into the render group, if you remember, here's sort of all of our SIMD intrinsics that we were doing, right? And the big thing about these SIMD intrinsics is, in order to leverage the SIMD unit, the SIMD operations on the x64 processor, which is what we are writing our code for, or the x86 in this case as well, we need to be able to process things in batches of at least 4 at once, right? We need to be able to do things in chunks of 4. Now, some of the stuff in here will be pretty straightforward for that, right? The other thing that we need to do is we need to make sure they're aligned, right? And we can work with unaligned data if we want to, but usually it's better for us not to, for cache reasons anyway, and also sometimes it's faster to do aligned reads and writes and so on and so forth. So what we probably want to do is we probably want to make sure that at the very least our temporary buffer here is aligned the way that we would want it to. And remember, we've already done some work to make sure that we can align it. So if we want to do that SIMD alignment and align things to 16 bytes, we actually can just go ahead and tell our allocator that we need it 16-byte aligned. So we already did the work for that, and it should be fine. And so the first thing I'm going to do is take this clear out the mixer channels thing. I'm going to go ahead and see if we can go ahead and make that 4 wide. So what I want to do is I want to say that we're never going to ask for an output sample count, right? That isn't going to be an even multiple of 4. So I want to say ahead of time, look, I'm just expecting you to always give me a multiple of 4 samples. So we might have to go back into the platform layer and ensure that it always does something to round it to that. So I'm going to put an assertion in here to force us to go do that work once we're ready. Now, I suppose now that I think about it, as I'm saying that in my head, actually I don't care about that at all. I thought I cared about that, but I don't really. These are temporary buffers. So really what we could do is we could just say, you know what? We have a sound sample count, and we really just need to make sure that this sound sample count can fit all of the samples in there, but we don't really care if we went over, right? Because when we copy out at the end to the 16-bit values, that's the only place we would have to care about that overhang for the per 4 samples. So what we could say here is we could go ahead and just round this to a power of 2. I don't know if we probably should. This was confusing people a little bit because I tend to type this in because it's kind of second nature to me a lot of the times. So I don't know if we have an align call anywhere in here. I don't think that we ever wrote one. Okay, so we have an align 16, right? And so what I think was confusing people a little bit was this sort of value plus 15 and not 15 kind of stuff. And someone asked a question on the forums. I explained it one time, and basically it was just saying that this is just saying, okay, I'm trying to round up always to the next nearest power of 2. I'm sorry, to the next nearest multiple of some specific power of 2. In this case, it was 16. And the easiest way to do that is to add 1 minus the power of 2 and then knock out all the bits that are below that power of 2. And I explained that on the stream one time. But really, you can think of this as a fairly generic thing. You can think of align n as like if you have a value and an alignment, right? Something like this, like align power 2 or something, I don't know, something like this. You can imagine, as long as alignment is a power of 2, you could actually write this macro to be completely generic, right? All you're trying to do is take that alignment and subtract 1 from it, right? And that produces the right thing in both cases, right? So you can actually round to any one that you want here. And I tend to like to have ones that are, just kind of the convenient ones that I tend to use. So I tend to do stuff like that. But you can think about it if you want. You can think about these as just being a generic way of rounding. As long as the thing you're trying to align to happens to be a power of 2, this will work. If it's not a power of 2, this trick does not work. And you'd have to do something smarter, probably actually using a mod to get it to work. But I'm not sure. There might be fancier tricks. There's some crazy arithmetic tricks out there that people have figured out. So you never know. Anyway, so if I want to take this sample count and produce a, like a sample count that's going to be aligned 4, to round that up, I can do that, right? So I can say, all right, I want to do a sample count aligned 4, and then I also want to do a sample count 4, which is basically going to be that divided by 4, right? In other words, I want to actually have one that's divided by 4, so that when I come in here, what I can actually do is make the channels actually be MM128s, right? So there actually will just be packs of 4 of these things to begin with, okay? And so what I'm going to do here is say that I want to allocate the sample count divided by 4 of these M128s, which of course each contain 4. So that will give me room for my mix buffer, right? And then if I want to clear it, right, I should be able to clear it pretty trivially. In here, I should be able to say, okay, I'm just going to walk through all of the values, and I'm just going to use mmset 1ps to make something that's just replicated a bunch of zeros, right? You know what I'm saying? Just totally 0. In fact, I could just do this like so, and just say, all right, you know what? We've got a 0, and these guys are just going to be equal to zeros all the time. Okay. So that would do it, right? And of course, I only want to loop over the sample count 4 version of it. That would clear all of my stuff out. Now we have to do a little bit. Oops. We have to do a little bit here because these are still, sort of working with them as if they are M128s. Or sorry, this is still thinking of them as M28s, and this is going to be reals. I'm just going to cast it for now, since that's free for me to do, and let these guys work in their normal way, so that I can just test the clear to 0 and make sure that that's working relatively well. So let's take a look. Yeah, so that's all good. No problems there. So the clear to 0 looks fine. Let's go down now to the bottom, and let's take a look at the conversion, right? And we have a clamp in here as well. So we actually had a little to-do that was like, hey, remember to go ahead and clamp these guys. So what I want to do for clamping those guys is I would like to sort of make some clamping information here, right? So something like max 16-bit, or max sign 16-bit, and min sign 16-bit, or something like this. Maybe max S16, min S16, something like that. So that we can put that clamp in as well. So what I want to do here is I want to set these guys to be the floating point, because remember, all of this mixing is taking place in floating point, but it's taking place in floating point versions of 16-bit values. So basically, we're not even converting. Remember, in the renderer, we convert all our stuff to the 0 to 1 range, or, well, I guess we even changed that to start working in 0 to 255 in a bunch of places. We're doing that same 0 to 255 kind of thing here, where we're letting it run from negative 32K to positive 32K, right? We're letting that actually take care of the mixing in that range instead of trying to bring things back to the 0 to 1 range, because we don't really have any reason why we need to bring things back to the 0 to 1 range. So when we talk about clamping of the values, what we want to do is clamp them we're clamping them essentially as 16-bit values, even though they're stored as floats. So we want to produce some floats that would be the maximum and minimum signed 16 values, if that makes sense. And so I'm trying to think of what the easiest way is to get those. I mean, really, it's just, I don't know. I'm thinking maybe the easiest way to do it would be to say, like, oh, I've got an S16 of that, right? That would be the minimum. And then I've got an X16 of that would be the maximum, right? I think that would probably give me what I wanted. But let's, since we've never done anything like this, let's do this first. Let me just let's see. Let's do it this way, just so you guys can see what I'm talking about here, right? There we go. And min max. Okay. Let's see. So can I actually make it do this? I don't think I can. Yeah. Well, I tried, and I unfortunately failed. I kind of just wanted it to look at these guys and do them as if they were, valid 16-bit values, so I could force it to look at the min and the max without me actually having to do anything, but it doesn't look like that's in the cards, unless I just am thinking about this slightly wrong. Basically what I'm saying is, let me comment these out. I'll show you what I mean. Okay. So if I go into the sound mixer here, or if I can go in anywhere, right? Like so. So if if I take something and I want an S16 value, right? I want a short value. If I was to take the 65536 divided by 2 here, right? Something like this. You can see in hexadecimal, let me see if it's not quite the highest. Why are you not? I want the highest value. Oh, because I actually typed a 2 by exactly. How to do that? 65536. So if I actually type the highest value there, right, that I could actually get in practice. Oh, okay. I just typed that wrong. There we go. So if I actually get the highest value that you can fit, and I guess what I could do is I can also show this in binary so you can see it. If I wanted to get the highest value I could possibly fit in a 16-bit value, it's going to be all of the binary places are going to be set to 1, except for the final one, right? Because if you're talking about a signed value, then as you get, once that top bit flips to 1, your value is now a signed value, a negative value, right? So this is the maximum value you actually could produce. So what I wanted to do, right, was I wanted to make it so I could do 7FFF. I wanted to make it so that would be the minimum value. So I think that would actually work now, yeah. So that was just a stupid mistake on my part, so it was fine. So if we want to make the minimum value, we could make it that way. Making the maximum value, what I actually want to do, I don't actually want to do it that way. I don't even know why I typed it that way to begin with. I guess it's just a bad, I'm just a, oops, sorry. That's not the min, that's the max. There we go. Wow, maybe my brain's fried today. I don't know why I'm thinking so slowly. It's kind of one of those days where, I don't know, the brain's just foggy. Anyway, so yeah, the maximum value, which we just showed, like this, right? If I look at that without the binary on, right, then that's the 7FFF, right? So that's the value that I would want for the maximum value. I don't know why I typed it in for the min. For the min, I just want all Fs, right? You know, I just want it to be flipped around. No, sorry, that'd be -1. So that doesn't help me either. Although, yeah, so I don't actually know. I guess I don't actually know why it wouldn't let me do FFF cast. I guess it's because there's really no way to tell it, hey, I wanted this value to be negative, right? But that's okay. So what I actually want is this, right? I actually want the highest positive negative value, which would be a 1 in the top and all zeros. I don't know if it would let me do that, though. Yeah, so it won't. But just to show you what that is, right? If I was to actually take this value, you know, 0x8000, what that actually is, because of 2's complement, which we've never actually covered on the stream, I think. So you might have to double check that guy. But because of 2's complement, the way that they tend to work with values that are in binary on CPUs is, unlike the floating point math, where you have a sign bit that literally just gets set or unset whether or not the number is negative, in integer math, they do this trick called 2's complement to make it simpler on the hardware, because basically you can do all the operations the same whether the value is signed or unsigned. And the math all works out exactly the same way. Now this is a little bit confusing, so I'll just kind of mention it briefly. I don't know that now is a great time to spend a bunch of time talking about 2's complement, but since my brain is fried anyway, obviously, today, maybe it wouldn't hurt, right? Is this the right thing? Hello, Mischief? Mischief takes a while to load our giant blackboard now. I don't think they were expecting people to use it quite like this, but we do. So, you know, I usually just tend to leave it running so we don't have to wait for this, but like I said, the machine accidentally logged itself out the other day, and so that was kind of unfortunate, to say the least. But anyway, so 2's complement. You know what? But I always spell complement wrong, so we're actually going to check that out. 2's, is it complement with an I? It's E. Okay, so I spelled it correctly. Good. But that's totally, I always spell complement the wrong way, since there's multiple of them. So all I was saying before was, you know, if you imagine, let's take the simplest case, or a very simple case, which would be like, let's suppose that we had a value that's only 4 bits long, right? So it can really only, represent values between 0 and 15 if it's unsigned, right? This is the 1-bit, this is the 2-bit, this is the 4-bit, this is the 8-bit, right? And so if it's unsigned, then the maximum value that it could support is 1s in all the places, which is 1 plus 2 plus 4 plus 8, right? And so that's just going to give you 15, right? It's you know, just basic math. So the question is, what if I want this to be a signed value, though, right? Well, if I want it to be a signed value, I need some way of telling the difference between whether it's signed and whether it's unsigned. And so what you could do is say, well, that top bit, right, is going to tell me whether it's signed or unsigned. And so what I'd like to do is make it so that I just can set that, you know, if I just think about that bit, if that bit is set, I know the value is signed. If that bit is unset, then I know the value is unsigned. That would be pretty nice. And that's the way that floating point does it, right? Floating point has the high bit, and it just sets it on and off directly. But what happens is, if we were to actually literally make that the rule, meaning, okay, this bit is now just the sign bit, but these bits still mean 4, 2, and 1, right? If that were the case, then the processor would always have to special case this bit, right? It would always have to go, if I have A plus B, where they're both these kind of numbers, it would first have to go, oh, is, what are the signs of these two? Like, is the sign bit set in both of them, or is it not set in both of them? Okay, well, if it's set in both of them or not set in both of them, then you can actually add the bottom together and then just leave the sign set the same. If it's not, you got to turn this from an addition into a subtraction, and right? It just gets kind of annoying. But it turns out that you can do a nice trick here with the way that you conceptualize the numbers. If instead of thinking of the negative numbers as the same as the positive numbers, but just with this bit set, what you can do instead is think of it as counting the opposite direction, right? So normally what happens is you have 1, 2, and 4, and the 0 bit gets set, on. Sorry, I should say the 1 bit. The 0 in the 1 bit's place gets set to on. That becomes 1, right? So in unsigned, right? Oops. In unsigned, I have 0, 0, 0, 0 equals 0. I have 0, 0, 0, 1 equals 1. I have 0, 0, 1, 0 equals 2, right? And I keep going like this. This is how I count up, right? Make sense? And I can keep going like this to get all the way up, right? And so as I go, I count up in unsigned. Now, if I wanted to do a signed value instead, right? If we were doing this trick where all we did was set the sign bit, you would expect it to, again, just look, this would just be ones the whole way down, right? And now it would be, well, there'd be no such thing as -0, right? But you'd have -1, -2, -3, -4, -5, right? And maybe you would have a -0, who knows, right? That's what you would expect to see. But, like I said, that would produce this kind of nasty special casing that has to happen in the processor, and they just didn't want to do that if they didn't have to, right? So 2's complement is a trick that says, no, don't do it this way. Instead of using that value for a -1, let's actually use all ones to represent -1, right? Why would you want to do that? Well, the reason is because now if you just implement your addition operations the same way, and so what you actually can do too here, as you can see, I'll take it a little bit further. So here you go. There's -1. You can see it's all F's, -2, right? -3, -4, -5, -6, -7, -8. And what you can see is it's literally just counting down backwards, right? And so if you look at what happens, right, you'd have, if I wanted this to be a -2, what I would do is I'm doing exactly the opposite operation as I was doing, before on these guys, right? In fact, I can probably do this in binary for you so you can see it a little bit better, right? Do you see how this is going? Like so? And the reason that they do that is because, well, it doesn't really matter to humans, because humans, we have to write a routine to decode this binary to print it out in ASCII form anyway. So, who cares about that? Who cares about the meaning of the numbers? As long as there is a way to know what they mean in human form, that's fine. What we actually care about is what happens to the arithmetic in the computer. Does it produce the right results consistently? And what happens is if you treat this as the encoding for negative numbers, right? Then what happens is all the arithmetic still works the exact same way, right? And I know that sounds kind of weird, but that's actually just what happens. So for example, if I were to take all zeros, right, and let's say we're doing signed arithmetic now, so that equals 0, right, and I were to add to it -1, right, then I would get -1, which is exactly what I would have expected, right? What I would have expected. If, on the other hand, I want to go ahead and add, -1 and -2 and expect to get -3, right? So I go in here and I say, well, all right, I've got -1, like so, and I got, well, not actually, here we go. I've got -1, and I want to add -2, right, to get -3. So what's going to happen here? Well, I'm going to go ahead and add these guys up, right? I add these two, and I just get a 1 in this position. I add these two, and I get a 0 in this position. But I have to carry, right? I get I have to carry the 1 again here. I have to carry the 1 again here, and I get the excuse me. I get the carry bit as well. You know what? Actually, now that I think about it, how do they do the borrows? I don't actually know how CPU vendors even implement this. Today is a weird stream. I don't even remember. This is like going way back into my like the crusty regions of my brain. CPU adder. I want to see how they actually do this. Because basically what's going to happen is they need to roll, the value needs to wrap, right? I mean, you can see this happen. So I know what happens in practice, but I don't know how they actually do it in the CPU, and I can't actually remember. So if we could take a char, for example, let's say I take something like this. This is definitely turning into a ridiculously off-topic stream. Let's say I take two unsigned integers even, right? So this has nothing to do with the 2's complement or any of that stuff. If I just have two of these and I take 255 and I add 3 to it, right? Or just even 2 to it, right? And I don't care about any of this. And so I want to get the result, and I do a plus b, right? So you can see what happens in here if I actually switch over to the audio, output playing sounds. So if I come in here, right, and I look at these two values, a and b, so you can see that when I'm going to, and I'll actually put these in binary as well. When I add these two in signed, right, what I expect to get is the value to wrap around, right? So when I add these two together, right, I'm going to get something that that equals whatever the wraparound actually is, right? So I should get 1 when that happens, right? And I do. So, yeah. So I don't actually know what causes that actual wraparound to occur in the other case. Well, I guess it doesn't. That just works fine, right? The ones add, those will carry, and it'll just carry all the way out. So that's actually fine, I guess. Yeah. Well, all right. So let's try one more. So let's suppose we add 255 and 255 together, right? I guess that works all the way out. This is turning into a Casey gets to experiment with things stream. But you know what? That's just how Fridays go sometimes. And also, it is boiling hot in here. It's getting really hot in Seattle in the summer, so like I am so in need of some air conditioning or something. But anyway, so if I do the 255 adds, so I think I was just asleep at the switch here. Yeah. Oh, duh. This is just me being dumb. Okay, good. This is like stupid Casey Friday. Because I was going to say, I didn't think they had to do anything special for the wraparound. They don't. This is 3 1s that I'm adding. How did I get a 0 here? I have no idea. That just should have produced a 1. 1 plus 1 plus 1, right, equals a 1 plus a carry 1, right? And that carry 1 then makes this equal a 1, which exactly equals -3, right? Oh well. So yeah, this is a stupid Casey Friday. I'm afraid that's just the way it is sometimes. You know, I'm pretty old these days. You know, these are the kind of days when I'm pretty old, so the brain is not what it used to be. Although I feel like I probably would make kind of careless math errors like that even when I was little. Like I was really bad at arithmetic in grade school and high school and stuff. Like, so this is actually the kind of mistake that pretty much Casey at any age would do. Like a little baby Casey in diapers, you know, that's a diaper Casey. There's the nipples. And then there would also be, you know, kind of like the old Casey with a cane or something like this, right? And a long beard, I guess, you know, and he'd be hunched over probably, right? Something like this, like that. I don't know, that's horrible. This is just, don't even think about these. But anyway, back to the point. So the 2's complement stuff is just an excuse for CPU vendors to not have to do any special casing for the math to work out, right? Because what ends up happening is if you just add these values the way you normally would, and you're a CPU so you don't make mistakes like I do, when you actually add the values, you end up with the right answer, even if you didn't know they were signed. So no one has to tell you that this is actually a signed value. You don't have to know that there's a special meaning for this bit. The arithmetic still just works out. And so I don't actually know who figured this out, but you know, somewhere way back when someone must have figured out like, oh wait, if we just treat negative values the same as positive values and use this encoding, then the CPU just always works, whether it's a signed value or an unsigned value. And that's why you don't need two add instructions. You don't need one add instruction for signed and one add instruction for unsigned. You can just use a single add instruction and it works, right? So the long and short of it is, all ones equals -1, whereas a one with all zeros equals the maximum value, right? Like negative, I guess 16 in this case, or I should say -15, right? Yeah, because you can't actually. So this actually also introduces that other dichotomy. This is kind of this encoding, this sort of the top bit means negative, and we count the numbers down backwards thing. That encoding is also why you always get one additional number in the negative space versus the positive space, right? Because you look at the positive space, the maximum number I could have encoded was this, right? So if I have the 1-bit, the 2-bit, yeah, this is not right. The 4-bit and the 8-bit, right? The maximum number that I could have encoded was going to be 7, right? Because this is a signed 4-bit number, right? So it ranges from -8 to 7, right? So I don't know why this is -8. I don't know why I said -15. Wishful thinking, I guess. So if I look at this, right, the bits here, I can't set this bit, because if I set this bit, the number would be considered to be negative, right? And that's, that's not what I'm trying to do. So I'm trying to set the maximum positive number. I can only do 1 + 2 + 4, which is going to be 7, right? But I can set this bit and all the other zeros to make the maximum negative number, and that is -8, right? Because you look at how far that has to count down, it has a pretty long way it can count down, right? It's still got all of these options. It still has 7 different options in addition to this one to count down, right? Another way to look at it is it doesn't have to represent 0, because 0 was representing the positive case. So you get one additional value, and that's why signed integer values are always like -n, to n-1, right? Whatever it is, whatever the range is, you can only go to one less than the maximum value in positive that you could have gone in negative. All right, so that was like the dumbest possible explanation of 2's complement, because although I guess my explanation wasn't awful, I managed to make so many mistakes in the actual arithmetic of it that it probably confused everyone more than it helped. But that's okay, because 2's complement is actually pretty simple. There's not a lot to it, pun intended. So if you want to just go look at a 2's complement webpage, it should have an examples for you without my math errors, and hopefully that would be clear. But the point is, I just wanted an easy way to generate what these are. And so what I would like to do is be able to say, oh, I've got a 16-bit value. So what I was hoping for is I could just say OX 88000 to say, why don't you just give me a 1 with 15 zeros after it in binary, so that I can just have the maximum negative value. Now I could just produce that value instead by thinking about what it is, right? I know that it's going to be I know that it's going to be this, right? I know it's going to be -32768. So I could just type -32768 in there. But since -32768 is somewhat hard to remember, I was just thinking maybe I could do something a little bit more clever. But what it seems like is the case that unless I want to get exceedingly clever, it's not going to let me do that, because you can see it worries about the cast trunking the value, because it's thinking that I'm trying to represent an unsigned value here, right? It's thinking, oh, he's trying to actually represent the positive version of that number, and if I were to cast that to a signed, I wouldn't be able to record it. So long story short, we can't do that. That's fine. So we'll just go ahead and say 32768 will be our value. So our min will be -32768.0, right? And our positive would be not this, because like I just said, you can't quite get there. This would be our positive value. So all right, 2's complement, what are you going to do? Sometimes you just gotta, sometimes the explanations on Handmade here are better than others. What can I say? That's the you got to take the good with the bad, the baby with the bathwater, all those sorts of things. So the good news is, if we have these things here, right, then clamping becomes really trivial. We've already done it. It's pretty straightforward, so we can clamp these guys once we are ready to do the clamping. But let's go ahead and work on the other part of it first. So what I'd like to do here is I want to go ahead and read from the source as M128s instead of casting down to reals and process 4 of these guys at once, right? Now the problem is we don't actually know, like I said, that we have a buffer that actually fits a multiple of 4 in there. We know that our reads do. We don't know that our output does. But what we can do is we can make it so that we know that it always will by forcing the platform layer to always give us a little extra padding so that we don't have to special case this loop, right? And so that's pretty easy, and that's something that we can do pretty easily in the Handmade platform stuff, right? We can just say, when we go to the sound output buffer, here we go, we can just say something like note, samples must be padded to a multiple of 4 samples, something like that, right? We could even make it bright yellow if we wanted to. There we go. Yeah, so we can do something like that if we need to. So let's take a look at writing this and not really worry about overwrite at the moment, because it may be that we don't really care about that at the end of the day. All right. So if we read in these two guys here, right, we've got one channel here, one channel here. These are floating point values, and so what we want to do is we got to convert them down to 16-bit, right? And so what we were doing here is we were just rounding them and then converting them. Now we know that we already know how to do this for the rounding, right? We've got that CVVT PTS, this guy right here, right? This is the truncating one, and then there's also a rounding one, right? I don't remember which one. Is it this one? That's the rounding. That's the truncating one. Convert API. No. Where are we? Where is our? There is a rounding one. Sorry. Convert PS EPI 32. I believe that is the one that would do the rounding for us. Am I wrong about that? Let's see here. Yeah. So this is the one that does the rounding, not the truncation, right? So that's the one that we would want to use. And so what we can do there is we can just read from the source, and this will do that rounding for us, right? So this will round the values, really pretty straightforward, just going to round the values. So now they become integer values, right? And so now what we've got here is M128i, right, for our source 0 and our source 1. So there we go. No big deal there. And then what we want to do after that is these are still, they're going to be converted from 32-bit floating point to 32-bit integer, and it will round them for us, and that's fine. But unfortunately, it won't actually convert them to 16-bit for us, right? And we need to output interleaved 16-bit samples. So what we need to do here is we need to down convert the 32-bit values to 16-bit values. And so this is the place where, I don't quite remember exactly which options we have, but this is going to be a pack, right? We're going to have to do one of those packs to pack down. So let's take a look at what we've got in terms of packing. We don't really want convert. Let's see. Store, shrink, compare, shift, set, random, move, logical, load, store, mask. Yeah, I don't know if the packs, where are the packs? I guess I don't know where the packs even are in here, so I'm just going to look for mmPack because that's what I actually want, and I won't bother. Oh, you know what I could do? I can use a little filter, mmPack. So let's see here. If we want to do convert packed 32-bit integers from A and B to packed 16-bit integers using signed saturation, and so that is exactly what we want, right? Signed saturation means that if the values were higher than 32 bits to begin with, they would actually get saturated out to 16-bit integers, right? And that's actually pretty awesome because that means that we won't even have to do a clamp, if you think about it, right? Because if the value is greater than our range of negative 32k to positive 32k, the signed saturation of the pack will just take care of it for us, right? It'll just threshold it down and we'll be done. So I think actually that's pretty handy. Much more useful than I guess I would have thought. So that's kind of nice. All right. So let's go ahead and make that happen. That sounds good, like so. So then we've got the combination of the two, but the problem now is they are not interleaved, right? The 16-bit values are not actually interleaved together. And so that, again, does not really help us because we've got now essentially what we've done so far, right? If you think about it, we start off and we've got some buffers that look like this, right? We've got L0, L1, L2, L3, R0, R1, R2, R3 in memory order, right? And these are all 32-bit floats. And so in memory order, not processor order, but in memory order now, once we do this pack, what we'll get is we'll get one, we'll get a nice single buffer that actually has 8 values in it, right? It'll have L0, L1, L2, L3, R0, R1, R2, R3. So that's great, and that's exactly what we want for we got 16-bit signed values now. But the problem is we actually wanted it to look like this, right? We actually wanted the things to be interleaved. We wanted L0, R0, L1, R1, L2, R2, because that output buffer is expecting the samples to be interleaved. So what we need is something that would pack these things together, right? We need something that would go, take L0 first and L1, like that kind of thing, right? And so, again, I believe we have pretty good options for that. Hilariously, after calling unpack, I think unpack actually would be what we would want for that. Well, no, I guess because that would be the high of two things. So no, we don't actually want unpack high. I guess this would actually be some kind of a 16-bit shuffle. How are we going to do this? I don't actually know if we've got what we may have to do before we do the convert. We may have to do something cleverer to interleave these guys. I'm trying to think, right? Because the unpacks that I know of and the shuffles that I know of won't do a 16-bit shuffle like that. There just isn't a way to do. I can't think of any way to do that offhand. Yeah. Because if you look at the options that we have for rearranging things, I'm pretty sure, like, what's the shuffle EPI in A and store the results in dest? So we can shuffle 32-bit values around all that we want. That's fine. What's PI 16? Shuffle 16-bit integers in A going and store the results in dest. So that one does only the bottom ones though, right? Or does it? Select immediate 1, 0, 3, 2. Oh, well, actually, this is kind of a bizarre instruction. Shuffle the 16-bit integers in A using the control in IMM8 and store the results in dest. And so it takes a look at the source and the control. So the control in this case refers to what though? The 1, 0. Okay, so the the control is the 1 and 0 bits, which of this, I guess, is what they're trying to say to the first 2 bits. And so in the case here, I guess they're doing a temporary. They're putting into a temporary and then returning the temporary out. So it's this part that's actually getting out of the control. This is a weird function. I've never called this before, but that is strange. So this is doing some extraction here. That's fine. And then we have the destination. This is just doing 16, 16. So it's only doing the bottom part of the destination, which is not really useful to us. So again, don't think that's particularly great. And we can do shuffle high and shuffle low. But again, that's not really what we want. So it doesn't super look like we have much in the way of options here, unfortunately. It looks like we would have to shuffle things ahead of time if we wanted to make this happen. So I'm just going to see if that's an option for us. I don't know. We'll have to think about it a little bit more, a little bit later on, if there's maybe a better option. But I think we might have to shuffle ahead of time. like basically put these guys before we pack them into an order that's more amenable. So interleave them ahead of time, right? We could do 2 shuffles and put them in the right order to basically do an L0, R0 kind of thing, right? And so what I'm thinking is that's probably what we need to do. So we do like an M128 just at the head end, where we say something like, okay, you know, we read out the source, the 2 sources, and then we do sort of a shuffle where we've got, we want to do like a RL0, like, I'm sorry, LR0, and an LR1, where we say, okay, let's shuffle these guys together. So we'll do an MM, I think it'd be an unpack, basically, where we're just going to interleave them, right? Because all I want to do is I just want to take these 2 values and pick one from here, one from here, one from here, one from here, which is the typical pattern of an unpack. So we do an unpack low. Where's our unpack low at? Our unpack low is right here, right? So we do an unpack low, and I guess I can leave that conversion in there as well, now that I think about it. The conversion's fine, right? So if I do an unpack low EPI 32, and I unpack the S, I guess we could call this L and R as well. These are the left channel samples, these are the rights. So we'll interleave the left and right samples there, and then do the high samples as well, right? And so again, that's just taking these 2 guys, right? And the unpack low will produce this part, right? So it'll take these guys and interleave them. Take one from here, one from here, one from here, one from here, and then the unpack high will do these guys, right? It'll produce, you know, L2, R2, L3, R3, right? Okay, so then when I've got those, then I can just do the pack, and the pack will just work, right? It'll just pack them down, and they're already in the right order. And so then I should be able to take sample out, and sample out, I can now just write to it directly, right? And so if I did M128i, sample out, and I don't know, cast this, you know, directly to it, right? I should be able to just say, all right, sample out plus plus is now going to write out is now just going to write out that S01 value, right? Okay, so yeah, again, we need to actually ensure that we're not going to write out of bounds there is the only thing, and we're not actually doing that yet. So because, like I said, if we're going at 4 at a time, that means there could be some overhang. So we're technically illegal right now, but we could try running it anyway. Maybe we'll crash. Who knows? So not quite right. I'm not hearing anything in the left channel, so I made some kind of mistake here that we need to take a look at. Once we do our packs, is this the right one, packs EPI 32? Did I specify the right one? We looked it up, but then I don't know if I actually, pack, was it EPI 32 or EPI 16? Pack the image signed. So that's the correct one, right? Saturated 32 and 16. Yeah. So that's the correct one. So I'm not sure exactly why I had a problem there. We converted our guys to 32-bit. That's what we wanted, right, of our sources. So that's good. We do our pack down to 16-bit signed values. And we've got our unpack lows and highs there to do them, to interleave them before we use them. So that seems like that should have worked. I'm not sure what the problem is there. So I guess what I'll do is, you know, you've seen me do this trick before. So I guess what I'll do here is something like this, set EPI 32, you know. And I'll do something like 0, 0, 1, 1, 2, 2, 3, 3. Of course, I always forget the reverse order thing, so I want to set them so that these are in memory order like that. So all right, let's see here. And these are like the left channel. So I guess I'll do them. Left channel is A, and right channel, whoops, right channel will be B, if that makes sense. There we go. And now, all right, we should be able to see these guys. And again, all I'm really doing here is I'm structuring the values in the registers so that I can see them properly, so that when they get converted down, I'll be able to see which values are going where, just to make sure that we aren't doing something stupid in the routine, right? That's really the only thing that I'm trying to do. Okay, so if we take a look at L, and I want to look at it as I16s, right? I want to look at it as dot M128I I16, right? And then I'll look at R as well, R. And if we look at hexadecimal, we should be able to see there that we've got you know, these values as 32-bit values there. And when we go ahead and do the unpacks, we should end up with these being shuffled properly. So if I take a look at just one of them, like LR0, we should now have A, B0, B0, A1, B1, right? And that does look roughly correct there. Let's see here, B1, yeah. And then LR1, M128I, I16. A2, B2, A3, B3. So that all looks good. And now let's take a look at what that actual value comes out to be after the packing. Make sure that's sane. A0, B0, A1, B1, A2, B2, A3, B3. So that looks totally right to me. That looks all packed up nice. So yeah. So I think we're in good shape here. I'm also going to just make sure we don't overwrite our bounds. Not sure what's going on there. What did I do? What did I do? Sample count 4 minus 1. I guess it's possible that sample count went, well, assert sample count 4 greater than 0. Why are we not hearing anything? What is happening? So I feel like that should be where, oh. Okay, so I guess the problem was just that that overwrite was probably overwriting something important in the buffer. So, all right, I take it back. I think our routine is probably fine. We just have to make sure we actually allow that padding to be padded out. So let's go ahead and do that over in the Win32 side of the code, right? And so where we do our samples, when we actually go ahead and alloc those, right? Let's make sure that we actually have those samples. Let's see. So what we want to do here when we do secondary buffer size, whatever the secondary buffer size is, we have to make sure we always align it by 4, just to make sure we've got enough room there. And actually, I guess that's not true. The secondary buffer size actually doesn't quite tell us what we need, because the secondary buffer size, we don't want to align that by 4. We want to make sure that the number of samples could be done by 4. So what we can do there is we can just say, well, 4 samples, right, times the size of a sample, right, which a sample is a U16. We know that we couldn't possibly need more than that overrun, right? And so we could just basically say we have max possible overrun or something like that. We could just say that we have that, and we always make sure that we have that much in there, right? So that would be fine. And if we did that, then I think we would probably be okay with the overrun, right? Yeah. Of course, also, it could have just been the mouse position. I forgot we left that hooked up. That is bad for testing. I guess if I just always remember that it's hooked up. Alright. So that's all good. And now I guess these clamp values, the whole thing that made me have to go on the stream and realize that my brain is too crusty to properly do 2's complement math without preparation, wasn't actually necessary. So we do not need to clamp. The clamp will just happen during the pack automatically, which is kind of crazy. So this is actually totally fine with this, because the convert PS EPI 32 after the unpack, when we go to this pack's EPI 32, when that takes it from 32 to 16, it's going to do the clamp. We don't even need to compare against any values. It'll just do it for us. So that's kind of awesome. I guess that's just the way it goes sometimes. So we can also, if we want to, do something like this. Store. Excuse me. Store. Is it EPI 32? Can I do that? SI 128. That's what it is. So if I want to store this guy out, like so, I should be able to do that. Just to say that, hey, these are aligned, by the way. Cannot convert 1 to pointer, right? Oops, gotta take care of that. And these are, oh, store PS, sorry. There we go. And for some reason, it always wants you to cast them to a float star, which makes absolutely no sense to me, because why wouldn't you want them to be the other kind? So there's the store, so that should be fine. And it is. And we can also do, excuse me, the same down here, where when we're loading these guys, we can actually just say, okay, we've got MM128S0, MM128S1, and that can be an load PS of this value. And again, have to convert it to a float star for no reason that I'm aware of. And that is it. Okay, so our conversion loop now runs for wide. Our clear loop now runs for wide. So the only thing that we really have to do now is we just have to make our mixing loop here run for wide, which will be a little bit more. So we can do that on Monday. And that one will be a little bit more complicated, right? Because we have to actually have our mixing loop right here. I guess, what did I, interesting. So this is our bilinear filter and our non-bilinear. I think we decided that the bilinear filter didn't actually help. But anyway, we have to do this, this work, right? So we need to do a devolume incrementer. We need to do a desample incrementer. We need to do these guys wide. And more importantly, we have to make sure that samples to mix is always going to also be 4 wide. Also, someone mentioned a bug that we have in here. Fix the both volumes end at the same time bug. So yeah, so I think like I said, shouldn't be too much longer. We probably would have finished it today if I hadn't gone off on the 2's complement tangent, which hilariously was not necessary. But yeah, but I'd like to save that for Monday, just so we don't eat up the entire time of Q&A on it. But that's basically all we would really need to do. The rest of this routine doesn't actually do anything with the sound samples, so it's literally just that one little interior part that would be relevant. So we would basically just be lofting these guys up to MM128s, and then we would have each of these things, would just be a mul PS and, to multiply the master volume by the volume, and then another mul PS to multiply it by the sample value, and then we would have to do, our incrementers would have to be 4 wide so that they would go the whole way. So really that, converting that interior of the loop actually would be extremely trivial. It's converting samples to mix to be always 4 wide. That would be a little more complicated. So there. That's, yeah. So there's that. The other thing is, I mean, we could just write it so that it doesn't have to be 4 wide, and we just have a mask at the end that we use, but I don't know. I feel like just writing it to work 4 wide is probably the right way, and just padding our sample buffers out so that the sample buffers are always multiples of 4 as well, if that makes sense. Yeah. And thinking about that, I think that will probably argue for actually making sure that the sample buffers are always 4 wide, so that, you know, if we go back out to the platform code where we do our output sound samples, or game output sound. Where is our output sound? No. Well, here you go. So when we do our bytes to lock and we compute out how much we're going to do, and we do this sample count here, I think what we're going to want to do is always just truncate that possibly down to whatever the next size down is that's aligned by 4. Because if we always make sure that we align the sample count down to 4, then all of these routines, all of the samples can always be playing in lockstep in that 4. So we can always grab 4, process 4, and nobody has to be finicky about the edges. And that means they could also always be aligned. No one would ever be doing anything unaligned, right? So I feel like that's probably what we will want to do on Monday. That's just my assumption. Okay, that's all there is to it. Let's go ahead and go to the Q&A, if that makes sense. So if you have questions, I guess I can go while the questions are coming in, do perhaps a little bit more talking about the 2's complement here, since I brought it up. And now it's all been paged into my brain. So if you want to see a complete example, right, the smallest one we could possibly do that would probably look useful is 3 bits. So here's the full 3-bit set, right? Right? So now we've got all the values here, right? So in unsigned, right, what are these equal to? Well, this is 0, 1, 2, 3, 4, 5, 6, 7, right? In signed, they are equal to 0, 1, 2, 3, and then when we get to 4, right, that now it's the sign bit is set, right? So this is actually -4, right? And then it counts down, -3, -2, -1, right? Does that make sense? And so what you can see, if we pick any of these two and add them together, we always get the right math, right? We always get the right math no matter what we pick. So if we pick this one and this one to add together, right? Although I guess I should pick things that stay in range, maybe, would be a little bit more, well, you know, you just have to understand that they wrap, I guess is what I would say. So let's say that we pick these 2 guys to add together, right? So if we want to pick these 2 guys to add together, I'd have 0, 1, 0 and 1, 0, 1, right? And so if I add those together, I get 1, 1, 1, right? And what's 1, 1, 1? Well, that's equal to 7, right? 2 plus 5 equals 7. That's exactly what we would think it would be, and that's all good, right? Now what happens if I do the same thing, but just considering the interpretation to be signed? Well, same is true. 2 plus -3 equals -1, right? And so you can kind of see that, like, really the whole deal with the 2's complement thing is just because since we don't care what these binary values represent, right? We can choose the encoding to be whatever we want it to be. Because the only time we actually end up caring about that value outside of the computer is when we go to print out the values, and we can have that routine do whatever we want, right? So it can decode them however it wants. So all we care about is that inside the machine, we have the most efficient way of building the CPU. And if we do it this way, it means we just build one adder circuit, one subtractor circuit, you know, et cetera, et cetera. And that way, we can get both positive and negative numbers with the same CPU gates. And that's pretty cool. Yeah. And so the same, I believe, is true for most ops that you would want to do. Like if you want to do multiplication or something like this, obviously, you know, multiplying by 1 and 0 will always work because that's going to be the same value in either case. But multiplying by, say, 2 would also, I believe, be true. if you take a look at what happens when you multiply by 2, I think you always get the correct values there as well. So for example, if you were to multiply 2 times -1, you would expect to get -2, right? And so if you take a look at 1, 1, 1, and I want to multiply it by 0, 1, 0, right? Well, I'm going to get something that looks like this, right? And this is obviously a carry. So if I take a look at the 1, 1, 0, here's my -1, here's my 2, and hey, 1, 1, 0 is -2, right? And the same thing if I interpret them the other way. 1, 1, 1 was 7. I multiplied that, right, I'm talking about in unsigned. I multiplied that by 2, I get 14, right? 14 is not representable here, okay? That would be, that would wrap around. But hey, guess what? If I subtract, if I actually look at what I would get if I were to multiply it and then, do the wraparound, I guess, does that actually work out right? I get 1, 1, 0, which is 6, right? Which seems kind of odd, right? Shouldn't I get, if I have 7 times 2 is 14, unless I'm missing something, 14 should be 14 mod 7. Let me see what this actually is. Let's add to. Because that is what the wraparound value is. So let's see if we can actually make that happen here. I want to make sure that's actually true before I say it. So if I do 2 times 7, right, in binary, there we go. And now I take 2 times 7 and I AND it. Of course, I don't actually know what the I guess I'm trying to think if there's any way I can approximate this, because there's no value obviously that would do that. I guess I could do it with the 255s. So I guess we could do that. So if I take an unsigned char, right, let's put this in code so it'll be a little bit easier, right? So if I take a U8 and I set that equal to 128, and I set another one, right, equal to 2, and I want to see what A times B is, I'm interested to know what that will actually do, right? And so let's do 255. In this case, what we did is we did 7 times 2. So what we want to do here is take 255 times 2, right, and see what it actually produces when we do the multiplication. Oops. And I want to make sure this actually produces something consistent. All right, so let's see here. So if we look at the binary, there we go. So it does exactly what we thought it would do. And so if we take 255 times 2, we actually get 510, right? And so if you take 255 times 2 and you mod it by the values we can actually represent, you get 254, right? So that is definitely what happens with the multiplier, which is unsurprising. But it's kind of a little non-intuitive the way that I was writing that out, right? Because we know what it should be equal to in that system, but you end up getting, I guess because there's sort of the phantom 8th value that's there, you end up getting one less than that encoded value, right? Because if you think about taking out that first 7, you actually take out the first 8, right? So if we look at like what happened with this 14 when we did 2 times 7 equals 14, right? And then we see what the value was. I was kind of thinking, well, okay, you're removing the first 7. You should still have 7 left over. But really, when you wrap, you're technically removing the whole thing. So it's actually 2 times 7 equals 14 minus 8 is the result you will get, right? Not 2 times 7 equals 14 minus 7, if that makes sense. So it's actually the full n of your bit encoding, whatever that is. It's 2 to the n for that bit encoding. So I don't know. So that's kind of a little wonky, but you know, what are you gonna do? Hey man, that's binary, right? That's just how that goes. But again, that's only if you're overflowing the values anyway. So point being, yeah, 2's complement. That was just the unsigned case, but 2's complement, and you could see the negative case worked just fine. So all of it's pretty straightforwardly just the case that whenever you do an arithmetic op, if you encode them this way instead of encoding them in the other way, right? The other way that I had talked about was if we had started doing it like this. So that was negative 1, that was negative 0, that's negative 1, this is negative 2, negative 3. That just does not help you, because then you have to special case the math, because all of the math you were doing on unsigned is going to produce the wrong results in signed, right? Because, hey, when we did stuff like, you know, negative, when we did stuff like this here, right, where we were doing 2 plus 5, right, or 2 plus negative 3, we're not going to get negative 1. We're actually going to get negative 3 for 2 plus negative 3, which doesn't really help us. Or I should say we were going to get 2 plus, that would have been 2 plus negative 1 equals negative 3, right? So that would have equaled 2 plus negative 1 equals negative 3. Which really doesn't help anyone, right? That's so you would have to special case the math if you didn't want to do it into 2's complement. So Cooper Caleb, why isn't 2's complement used for floating point numbers if it makes signed arithmetic easy? Well, I guess, to be honest, I don't know. I'm not enough of a low-level hardware-y kind of guy to know the real answer to that question. But I would suspect that the reason is because in floating point, you are never multiplying values that aren't in the range of 0 to 1. So or operating on values in that way. So I don't know that it actually would help you, because you already have to deal with the fact, yeah. So let's think about this. So the way a floating point number is typically encoded, right, is the sign bit is 1 bit, always. Then you have the exponent, right, which is some number of bits, right? And then you have the mantissa, which is some other number of bits, right? And this is always like, usually there's an implicit 1 here, so this is usually 1 point something is what's encoded in here, right? And then this is just telling you what the power is. So it's like 1 point something times 2 to the whatever the exponent is, right? And so why you don't use 2's complement here is, I guess, I'm trying to think, but you know, once you have floating point values, I guess when you multiply 2 floating point, or like, let's say you're going to add 2 floating point values together, right? What's going to happen is the exponent itself is what's going to actually go up or down based on wrapping. So if you have, I feel like if you have a negative number, you've got to know what to do with the exponents properly. So I feel like, I don't know. I guess with the caveat that I just said, which is like I'm the wrong guy to ask, I would suspect that the reason is because the exponent is pulled out, it's not going to just work either way, right? So I feel like you probably would just it's probably the exponent that actually is the thing that's going to do that work. And so, you know, I wouldn't be surprised if you wanted to store the exponent in 2's complement, which I guess, you know, I don't even know. Is that what they normally do? It's been a long time since I've looked. Floating point 2's complement exponent. Let's see here. That is not actually how they are stored. That is something else. This is not what we want. Let's see. Floating number is exponent is biased. Sort off to the actual value by the exponent bias. So because there's signed values in order to be able to represent both timers, but 2's complement, you said yes. Solve the problem. This exponent is restored. Adjusting its value to put within unsigned range. So it looks like... Interesting. The usual representation for signed values would make comparison harder. Okay. When interpreting the floating point number, the bias subtracted. So it looks like, at least in standard IEEE, no, they don't store that in 2's complement either. But it's kind of cryptic. They just say would make comparison harder. So again, we probably want to ask someone who's an expert in this thing to have an opinion on it, because mine is kind of not worth anything. So yeah. So I guess they do not do that, but I don't necessarily know why. So what they do instead is they just store it, you know, it goes from 0 to something, you know, like if it goes from 0 to 255 or whatever, or 0 to 128, they're just like, oh, well, the first 64 values are positive and the next are, you know, or the first 64 values are negative rather, and the next ones are positive. So we assume that it's always, you know, the value plus 64 is what we actually encoded. Poo Shoes, are you not going to profile it to see how much faster it gets? No, I'm not going to profile the audio mixer, not at this point anyway. Like I said, I'm not really thinking of optimizing it. I'm just trying to make sure that it can run 4 wide. When you implemented streaming in chunks of audio, I believe the code actually loads the entire file with a platform layer virtual act for each chunk. Is this just an artifact of the debug nature of that code? Yes. So, like I said before, all of that loading code is going to be replaced with just pulls out of the asset file. So we don't care what that does. As debug load wave and debug load bitmap are complete throwaway. They can do whatever they want. They can allocate all the memory in the machine. As long as they don't crash our code, we don't care what they do at all. They just need to get us back the data for testing. Does the audio make the frame rate in debug mode? Yes, when we don't run, it's really just the renderer that is the that's the slow part, right? So because when the renderer is running in debug mode, it's much slower, and that's, you can see how slow it is even at the lower resolution. So it makes the frame rate just fine if we turn it down the resolution. So you can see this is running in low res right now. But when we turn it up to 1920 by 1080, that's when we, in debug builds, it won't run fast enough. In release builds, it runs just fine. So yeah, that's just the nature of a software rasterizer. It needs to be optimized highly, right? So one thing I was saying before, and I think we could probably do this pretty easily, I suspect. I mean, I guess I don't know, but like one thing that I was thinking we could do pretty easily is, in our build right now, you could imagine pulling out a just pulling out the compilation step for just the render code, if that makes sense, and making that compile with optimizations on. And I don't know if that's, you know, the most efficacious way to do it or anything like that, but you could imagine doing it so that we do something like handmade optimized.obj or something like that. And then we did, you know, this sort of nonsense here, right? Handmade optimized.cpp. And we did something like, you know, don't actually link that guy, just yeah, don't output any of this stuff. and just output an object file. I think that's -C is usually the thing for that. Let's take a look. Code generation, where is the actual call for that? No, C is don't strip comments. That's not going to help us. I just want to build just an OBJ. What would I do for that? Let's see. Linking LD, no, that's not what I want. Miscellaneous, no. Let's see. Output files, code generation. I'm not seeing it. Let's see. There should just be a way for me to just. I haven't done this in a very long time. I just compile everything, but there's just one flag that you put, which is just like, hey, by the way, just compile just to when OBJ. Don't produce an executable. Don't do anything else fancy. Can I just search for it? CL type to less. Nice question. And if I search for OBJ, no. Maybe if I just do /F0, it will just, and specify the output object file name, it will infer that that's what I want to do. I don't actually know, but let's try it, right? -FO, and there we go. So let's see if that does anything for us. -O2. And if I just make in here handmade optimized.cpp, right? What happens there? Looks good. So let's go ahead and go into render group. And, you know, if we were to pull this draw rectangle quickly out here, let's see. There we go. Would that work? I don't actually know. So the first thing we'd have to do is we'd have to include like handmade.h probably. And the other thing that we'd have to do, oh, this would come in here, right? And declared but not defined. We would have to deal with a bunch of annoying things like the fact that I declare some statics that don't get called, unfortunately. But that would be mostly it. So all I'd really have to do is in handmade.h at that point, I would just have to say, or I guess in handmade render group, maybe, I just have to say, hey, you know, there's this file that you're going to link with. It's external that you're going to link with. And there you go. Unresolved transition will draw a rectangle quickly. That's true because of this. So all we would really have to do now is figure out how to get around that static function. I'm not sure exactly what to do about that. Probably I would do something like this, where I would go, okay, wherever internal is actually gets defined, which is probably in handmade platform. Wherever internal gets defined, I would do something like this. If not defined internal, define internal, right? Like that. And then that way you could just say in the optimize thing, oh yeah, all that stuff I said was internal. I didn't really mean it. You know what I'm saying? So yeah, so we could definitely do it that way. We've got debug global memory is a unresolved external, so that's got to be an extern debug global memory. So let's take care of that. Debug global memory. Let's see here. Debug global memory equals memory. Why is that? That's an extern, though. I don't know why that is not. Why is that an unresolved external symbol? Oh, because it's still trying to build the whole thing, isn't it? Let's take a look. I think this is almost it, though. So yeah, if I get rid of this, yeah. So I just need the switch now that'll tell it, please don't build a whole thing. I don't want, don't link. Can I do that? How do I not link? Let's see here. CL compile C file to OBJ. That's all I want. It is /C. But it didn't seem to, that didn't seem to be it. Am I nuts? So confused right now. Oh, but that was it. So if we want to, that's one thing we can do. And I think that should fix it for us. So let's double check. Min32 Handmade. So with optimizations on, now that one file that to draw a rectangle quickly should be optimized. So if I go ahead and look for the 1920, if we switch back to high res mode, let's see if we can run at good speed. Yeah. So that's probably what we should do, is leave the build that way. Because that way we've got one file that we can just always leave optimizations on for. And so only when we're actually debugging that will we ever have to actually switch out. And everything else can always just be in debug mode, because our render loop is the only thing that needs that optimization. So. Cuber Caleb, if 1111 is supposed to be less than 0000, then how do number comparisons work on the CPU level? I believe that number comparisons are special cased. So those are not generic, if that makes sense. But you can pretty easily take a look, actually. So what you can do is, for example, if you want to look here, here's assigned 8-bit value, right? -100. Here's another one, right? And then here are two unsigned ones, right? And so if I do something like B32 AB equals A less than B, CD, C less than B, right? So if I do that, and then step in and look at the code, right? What we can see here is what the assembly actually produces. So if you right-click, and this is a good thing to do, anytime you're curious about this stuff, just take a look at what the assembly does, right? Just take a look. And then we can see. So let's take a look. We go ahead and do move SX. Move SX, we load in the A and the B, we compare the two, right? EAX, ECX, which is just trying to see what these two values are actually looking like. This is the sign comparison. And then we do jump greater than or equal to, which is what we would expect. So they do exactly the same thing. So they must be able to do, the comparison must do like a subtract on them that would then, it would then look to see, in fact, now that I think about it, that'd be fine, right? Because what's greater than, less than going to actually do? It's going to do, it's going to do probably some kind of like a subtraction on the two values, and then look to see whether it's greater than or equal to the high value, right? Well, let's think about this. I don't know. It's a good question. Let's take a look. But the answer is, you can kind of see here, comp JGE jump, right? Comp JGE jump. So it does not care in any way which is which. So let's take a look at that, that instruction. Comp x86. Compare two operands. So let's see here. Sets the status flags according to the results. The comparison is performed by subtracting the second operand from the first operand and then setting the status flags in the same manner as the sub instruction. When an immediate value is used as an operand, it is sign extended to the length of the first operand. So yeah, so it looks like, to me, and these are encoded the same, 3BC1. It looks like to me that that subtraction actually just works, right? Let's see here. So source argument sets the status flags by subtracting the second number from the first set, and then saying, let's see. So let's see if we can make sense of that by looking at the table, right? So what I want to know, right, is if I subtract one value from another value, if I want to do a less than comparison, I want to know if these two values are less than each other, right? Well, if I go ahead and subtract the two values, like, you know, let's say I want to know if -3 is less than 2 or something like this. So I subtract the two of them. If I do 2 minus -3, that would actually wrap me, I guess. I guess I need smaller numbers here. So let's say I do 2 minus -1, which would put me up to 3. In here it would be 2 compared to 7, right? And that would also put me up to 3, right? Due to wrapping. Now, if I were to do the opposite way round, right? So I was to do 2 compared to -1, so I'm going to do -1 minus 2, right? That would put me up to -3. And same here, put me up to 5. So I wonder if you can basically just do, is the value, right, after I do the subtract, is the value negative? If the value is negative, then that's my answer. If the value is positive, then that's my answer, right? Greater than or less than. Because, yeah, if you think about it, that should just always work, right? Because if the values, we don't care whether the values are signed or unsigned to some degree at that point, as long as that behavior is consistent. So yeah, I think that's actually fine. If I want to know if 2 is less than 5, right? Let's say I do 5 minus 2, that equals 3, right? If I do 2 minus 5, right? So 2 minus 5 would be 1, 2, 3, 4, 5, right? Is that correct? 1, 2, 3, 4, 5. I think that's right, right? So yeah, it totally, I think that totally works. So again, we're kind of out of time, but like I think it looks like they don't have to be special cased at all. It looks like you could just literally use the signed math on any value when you do the comparison, even though it's unsigned. And then whether or not the value would have been negative in signed tells you the answer of the comparison, whether it's signed or unsigned. It's kind of magical. Do you have any tips for speeding up compile time when using multiple translation units? Yeah, a few, but it depends on the circumstances. That'd probably be a better question for when we have more time. It's move SX for signed. Well, but that doesn't really have anything to do with it, Sean, though, because that's just making sure that it sign extends the value, right? That's just making sure that because we're doing these on not on 8-bit registers, right? That's just making sure that it loads in the values sign extended. I don't think it changes the way the comparison works at all, if that makes sense, right? So when it loads in these guys, right, it's gonna, if we go to disassembly, when it loads in these guys with a sign, it's just gonna sign extend them, right? That's all that's doing, because the value was only 8 bits and now it's sign extending, right? Same thing with these guys, sign extension. So I'm pretty sure that that doesn't affect this at all. That's literally just because of the fact that it needs to sign extend them, if that makes sense. All right, we have come to the end. We have come to the end, folks. Yeah. So, not the best Handmade Hero stream. I was kind of out to lunch today, it's true. But that just happens sometimes. You know, can't always be on top of it. And especially because it is so hot here. I am literally melting. Well, I guess I'm not literally melting. I just feel like I'm literally melting because it feels like my skin is melting off me in a very real and literal sense. Okay, let's get rid of these guys here. And let's leave that guy as is. We can also, if we want to, maybe, let's see, common compiler flags. What we could do here is some kind of an OD02 thing. I don't know how we want that to play out. I don't know how you tell it I don't care about that. But we can worry about that in a future stream, I suppose. So, okay. We're all good. I guess I don't want to actually exit. We saw how long it takes to load Mischief, so we'll just leave that up and running until Monday. And we'll go ahead and close these guys off. All right, thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along with the source code at home, you always can. Handmadehero.org, you can pre-order the game, comes with the full source code, and you can go right ahead and tweak it, play with it, experiment, see how it goes, which is a great way to learn from the stream. We also have a forum site. You can ask questions, get ports to Mac or Linux, and stuff like that if you're trying to follow along with those. You can also see an annotated episode guide maintained by the community. It's pretty cool. We have a Patreon page if you want to support the video series. We have a tweet bot, the tweet schedule you if you're trying to catch us live. And in fact, now would be a good time to subscribe to that because this weekend we'll be posting the schedule for next week, as we do every weekend. And the tweet bot is what will tell you when the video stream is live. So we'll be back here Monday, and I will go ahead and drop the main mixer loop into SSE, and then we will pretty much be done with audio. I think there's not really much else we want to do. So we'll be able to ping pong back to our asset loader, button up how we want to do the memory, and then define the asset file, and that'll be it. And then we can finally be loading out of a real asset file. I'll make one for us, and then we can party on it. It's gonna be pretty wild, actually. So many of these things getting checked off. Audio is gonna get checked off. Asset loading is gonna get checked off. Render is actually not that far from getting checked off. We just gotta go work on the lighting a little bit. Lighting particles. This is gonna be good. We're getting there, people. We're getting there. Slowly but surely. Just like the little turtle. All right. So that's about it. I hope to see everyone back here on Monday. Until then, have a great weekend. And yeah, if you're doing any coding this weekend, best of luck coding to you. I will be doing some coding this weekend as well. So hopefully I'll see you on the Twitters. Stop by and say hi. Take care, everyone. We'll see you on Monday.